Good afternoon and welcome to, whoops, there is some echo. Good afternoon and welcome to MAE 113 class calculus for the liberal arts. My name is Richard Kohar and this is lecture 27. And in today's lecture, we're going to be covering the derivatives of the exponential and logarithmic functions. And excellent. Thank you for giving me the thumbs up that the audio is good. We'll be covering, I think it is section 6.3 in the textbook. So in section 6.1, we covered the exponential function, and we covered logarithmic functions in the previous class. But I think I have just a little bit of house cleaning before we move on, because I'm not sure if this was covered in your previous courses. So we had the laws of exponentials, which we had done previously as review, but I'm not sure if you had seen the laws of logarithms. Just a show of hands in the chat if you know what I'm talking about in terms of what the laws of logarithms are. And it's just, let's see what other people say in the course so far. Seen them, but I don't remember them much. Okay. Well, that's good. We'll review this. Maybe it's a bit rusty. Maybe not a lot of people I vaguely remember some. Okay. Well, the nice thing about this is there's only 3 of them. They kind of start off with assuming that for x greater than 0, so we got some positive numbers, we have y is greater than 0, and we'll say that r is a rational number. And so the first rule, high school is much further away for some than others. Well, and again, it's probably, unless you're in a higher year number, you might not have seen logarithms in a while. And again, they're quite useful. We use them in statistics for when we're dealing with likelihood functions. And we use them to help us solve some likelihood problems, or sometimes logarithms are used because we perceive things logarithmically. For instance, light, we perceive light on a logarithmic or an exponential scale, that for you to perceive light at a certain level, that you have to double it, and to perceive another kind of double of that, you have to double it again. So while you think that you had increased the volume by you had perceived it that it's twice, really you had to increase it 4 times as much. Same thing with amount of light. But we'll get into some of those applications later. But first I will review the laws of logarithms. So we have, if I have a logarithm to the base b, and it's multiplying x and y, then if I want to split them up, it's just adding them together. So the log of b of x plus log b y, that's it. So if they're multiplying them, I'm just adding. I can split them up with addition. The second one is, if I have log base b, and I have a rational function like x over y, then I can write this as a difference. So the log b x minus log b y. And the last one, we have log b x to the r, and so r is our rational exponent. What's nice about this is this one says that I can actually put the r in front. So I have r times the log of b times x. Sorry, log b of x. Okay. So in terms of that, here's some examples. And so like the instruction would be like rewrite. So we can have log to the base 2, and let's say of 6x. Well, we can equivalently write that as, using rule number 1 here, that it's the log base 2 of 6 plus the log to the 2, and that will be x. So we can split those up. Let's see what's the next one we can do is, I have log of 5. Now notice the same thing is that the base has to stay the same. So it's not like I'm changing the numbers or I'm changing the bases. It remains the same. So if you wanted to go in reverse, like you wanted to collect logarithms, you would need to make sure that the bases are the same. Okay, so let's do this one. So I can rewrite this out as a sum, just like this one up here. So I can write it as a sum plus log of 5, sorry, log base 5 of y to the 6. And then applying rule number 3, I can actually bring that exponent out in front. So right here, I can have that 3, that comes down in front. And log to the base 5 of x plus, this 6 can also come down in front, so 6 log 5 of y. Wouldn't the change of base also be a law? Yes, you can think of it like that as well. So I mean, like if you really want to, like if you have log base x, then I could write this over here. Log to the, I'm going to use a different number because it doesn't have to be the same base. There we go. To the b. So you could do something like that for your change of base. And again, most people, when they ever write log, it usually means that it's log to the base 10. Usually. But again, like I said, make sure that you check your books because they may use a different base. Okay. Let's do one more example. We'll use log to the base 10, and we'll do AB over the cube root of c. And same thing what I can do here. I can do log base 10 of a plus the log base 10 of b minus, because I'm doing the difference part now, so I'm doing the division. So it's minus log to the base 10 of the cube root of c. Now, of course, the cube root of c is equal to c to the 1/3. So that means that I can actually bring that 1/3 out in front. So just kind of rewriting the first two terms. Minus 1/3 log 10 to the c. Okay, so those are just kind of like straight applications of the rules. Another way, again, for a straight application of the rules is to rewrite a string of logarithms into a single log. So for instance, I could have, express as a single logarithm. So this one I have 3 times log of 2, or sorry, log base 2 of x plus a half log to the base 2 of y minus 4 log 2 of y squared plus 1. So I guess the first thing that I'm going to do is I'm going to apply my third rule right here. So I'm going to bring that r up. So in this case, I have this 3 will come up so that this becomes x squared, or sorry, x cubed. So that's what I'm doing right here. I'm taking this, and this is rule 3. Same thing here. I can have log 2 y to the 1/2. So again, same thing. And same thing here. Let's just do one more. I'm just going to rewrite just using my exponent laws. There's a log to the base 2 of y to the half, so that's just square root of y. And what's the last thing is we can apply then our rules 1 for this part and rules 2 for this part. So in the numerator, I'm going to have x cubed plus, or sorry, x cubed times square root of y. So it's x cubed and the square root of y all over, because I have the negative now here. I'll write that into the denominator, and I'm left with y squared plus 1 to the 4th. Okay, so we've just reviewed some laws of logarithms. Because we'll need to do some derivatives, and we'll need to rewrite the function sometimes so that it makes it easier for us to solve. So sometimes just doing a couple of steps beforehand to simplify the original function can make it a little bit easier for us. Okay. So now that we got those laws either recalled or we just saw them now, we're going to run into this. Okay, so we had our function, and we had b to the x, and that's what we call the exponential function. Okay. And so like the title of our lecture is what is the derivative? So what is the derivative of an exponential function. Oh, sorry, would we not simplify the... Okay, excellent. Yes, because this one just comes up to the top here, and that still sticks all together, and that whole term goes into the denominator. Yep. What is the derivative of an exponential function? Okay, so if we, we're going to just, part of this is going to be review, which is what is our definition of the derivative? It's that limit as we let that delta x, that change in x, goes to 0 between some value of the function with a small change, and we're going to look at what that change is. So the original value, and then we're looking at that value plus that difference, or that change. And then we're going to let that change go really, really small. So what does this mean here? We're going to start to substitute in our functions here. So in this case, if I have f of x plus delta x, that means that I have b to the x plus delta x. So I can substitute that in. So for this part right here, that's b to the x plus delta x minus b to the x all over delta x Now the next thing that I can do is, if I have bx plus y, that is equal to b of x times b of y. That's our exponential rules. So that means I can split this up so that I get b of x times b to the delta x minus b to the x all over delta x. Then the next thing that I can do is I can factor this out because I have a b to the x. So I have to keep writing my limit. I haven't taken the limit yet. So b to the x. And so I'm going to factor that out. So I'm left with b to the delta x minus 1 all over delta x. Now, because this b to the x doesn't have a delta x, I can actually pull that out in front of the limit. I don't have to worry about that. Or if you're really concerned, what I've done is I can apply the limit to each of this, so this one and this one. And because the limit as delta x of 0 of b to the x, that's still just b to the x. So everything is legal. So I'm left with this. So now we're kind of stuck at this point right now because I have this limit here that I don't know how to solve. I have to do a little bit of an investigation. Now, again, you're not going to have to do this on the test. This is to show you how we're going to get to our rule or the derivative of the exponential function. So what I'm going to do is we're going to look at, well, we were using b here, and that's an arbitrary value. But for instance, let's look at f of x, so at 2 to the x. And on this side over here, I'm going to look at the function 3 to the x. And so what that means is I'll have this derivative that's equal to 2 to the x, the limit as delta x goes to 0 of 2 to the delta x minus 1 over delta x. And same thing over here. I'll have 3 to the x, and the limit as delta x goes to 0 of 3 to the delta x minus 1 over. So yeah, this is the issue that we have right here. We're looking at those values right here. So what we'll do is we'll create a little table. So those are the values that we're interested in. And what we'll do is we'll do it for 0.1, 0.01, 0.001, and 0.0001. Now I'll pull out my calculator, which is going to help do some of the arithmetic or the calculations. So in this case, hopefully I remember how to use this calculator in particular. But I'm going to use 2 to the, we'll use x. So 2 to the x minus 1, and we'll divide it by x. And we'll do a calculate, and we'll do it for 0.1. So that gives me a number of, say, 0.7177 for 0.01. Oops. 695, let's say 6.001. And lastly, we'll do it. Oops, did it give me my, there we go. Okay, and then the other one that I'll do is I'll do it for 3. So 0.1. Did I do it 4 times? Oh, there we go. Okay, so what we showed is that this is approximately 0.693 for this one right here, and over here this is approximately 1.098. So what we have is that if I take the, for this one, the derivative of 2 to the x is equal to itself, 2 to the x, times some number. Oh, maybe I'll say that it's approximately equal to 0.6932, and the derivative of 3 to the x is equal to, well, approximately equal to 3 to the x, so itself, times this number out in front here, so 1.0987. And you're probably thinking, okay, well that's not nice. How are we supposed to be able to do this on the test? And you would be, that's a very good question. And I would say, you know, in math, we wanted something to be a little bit nicer. So it turned out that this limit here, we had this limit that we were working with when we were finding this. This limit didn't work out very nicely. Now, again, we can have some wishful thinking, like, wouldn't it be nice? I almost feel like this is the beginning of song lyrics. Wouldn't it be nice if this was equal to 1? And we'd say, yes, Richard, that would be great. Then we wouldn't have to bother with doing any of those, pulling out the calculator and doing a ridiculous amount of calculations. So what we did see, though, from our little calculations here was that the value of it being 1 for this, to get this to equal to 1, the base is between 2 and 3. So if I picked the base to be 2, I got something like 0.693. And if I picked the base to be 3, then I got a number of 1.09. So it has to be between 2 and 3. So, you know, from the calculator, or from the calculations, we know that to get this to equal to 1, that the base is between 2 and 3. Okay. Oh, okay. There we go. So we know it's between 2 and 3. And this number is traditionally called E. So E is such a number. So E is the number such that the limit as delta x goes to 0 of e to the delta x minus 1 over delta x is equal to 1. And that e is approximately 2.71828 ... It goes on forever. It is what we call a transcendental number. So it's very similar to pi in that it never repeats. It's ongoing and very common. So like if should be able to, on a calculator, you'll find it. There's either the x here or e. And if I punch that in, it'll give me a very longer expansion of it. There's a lot of 8s, but don't be fooled. It is a transcendental number. Did I write it down correctly? Good. Okay. So, okay, you're going like, so what? What's nice about E then is that, so this means so I have f of x is equal to b of x. So that's what I have for my derivative so far. Okay, that's pretty ugly. But when we look at this case of e to the x, well, that becomes e to the x, and from this part right here, I've already said that e is such a number that that limit here is going to equal 1. So it's times 1, or that's equal to e to the x. So just again, to drive home the point, I have this function e to the x, and the derivative of itself is e to the x. So it's a very easy function to remember for its derivative. Is everyone okay with that one? Yes, no? How many people have seen e before? It's a little quiet in the chat. Just a poll. Just someone just tell me if you've seen e before. I think I'll get it when I see it in use. Okay. I have, yes. Excellent. Okay, good. So, you know, e would be like any other function. You know, we know what the base is. So for instance, I can give you a quick sketch. Some people said no. Okay. Also have not. Okay. So again, I can do a quick sketch for you. So I can tell you, so if I did this at 1 here, oops, and again, I should move this up. There we go. Sorry, sir, I still don't understand why it's important or relevant. Ah, okay. Well, we were looking at the exponential function, and the reason for that is we were looking for the derivative of the exponential function. We're going to get to it in later applications, but we've heard a lot about it for COVID in terms of exponential growth or an exponential curve, and because we're in calculus, the question that we'll always kind of ask for is, what is the derivative of it? You know, what is the rate of change of the exponential function? So that's what we started out with. And we started out with that derivative. We took our usual definition of the derivative, we worked it out, and we got stuck at this point. We got stuck right around here. The limit as delta x goes to 0 of b to the delta x minus 1 over delta x. So what we had done is we started to look at it numerically. We found that if we wanted this to be 1, if we want that limit to be 1, what we found is that by looking between 2, making the base of 2 and 3, that limit would be between would be 1. So then what we did is we said, okay, we're going to just set it equal to 1. And that base is going to be, we're going to call that number e. And so e is that number between 2 and 3. And actually, it works out to be 2.718. And that is the base. So that base will give us that sir, why do we want the limit to equal 1? Some of it we were looking at because math people are lazy. We wanted it to work out nicely. So what we said was, what base would that give us to make sure that equals 1? And what we found out is that that base is 2.718. Now, again, you're probably asking me, okay, but how do we solve this how do we find the derivative for arbitrary bases? We'll get to that point. But we're going to look at this small we just showed that we found an interesting case where the original function itself is equal to the derivative. So that's kind of the remarkable part of it. So e to the x is its own derivative. And again, we're talking about exponential growth. And okay, so before we get to that, I was going to just do a little sketch of what this would look like. So around here would be 2. So here is 1 and 2 and something like that. So this would be like 2 to the x. And for e, we know that it's about 2.718. So that means that it should be, if this is my 2 and here's my 3, this is close to around here. So I need to make sure that I can go through this point, up through here. And so there's like e to the x. And again, it would be just a little bit less than the 3 to the x curve. So that's kind of the cool thing about that, is that if I had drawn this well, that the slope of the tangent on this e to the x curve is equal to that value. So again, at this point, if I had picked that point right around here, which is around 2.7, that the slope itself would also equal 2.7. Okay. So what we'll do now is we can do a little bit more derivatives using e. So we're again looking at this function, say like f of x is equal to e to the x, or you can think of it as a special, it's a exponential function, so it's 2.718 ... all to the x. So again, we can look at doing some examples. So let's do this one. E to the 3x squared plus x. And in this case, to find the derivative for this, we have to use the chain rule. So using the chain rule, so in this case, we'll say that our e is our outside function and our 3x squared plus x is our inside function. So here is our outside function. Because again, people want me to use more colors. And here's our inside. So for the chain rule, what that says is that I need to take the derivative of the outside function So that's the derivative of the outside function times the derivative of the inside function. So we know that the function e, the derivative of itself is still just e. So the derivative then works out to, for the inside, is e, and we leave the inside alone. And then we just have to take the derivative of the inside. So in this case, it's what's in the exponent. So we have 3x squared plus x. So that gives me 6x plus 1. Okay. Another one that you might know, might run into, is if we looked at the derivative of e to the minus x. And so again, I can look at that as I have the derivative of my outside function, so that's just itself, e to the minus x, times the derivative of the inside function, so this would be my minus x. So in this case, the derivative of minus x is minus 1. And we can rewrite that so that I have minus 1 over, and I have e to the minus x. So I can also write that as 1 over e to the x, like that. And again, this is also equivalent to writing 1 over e to the x. So again, you're just thinking e is a constant. So if you see the, you're seeing just that as a number, and then it's raised to the x. Again, the same rules apply for your exponents. I probably then should explicitly state something like this, which is if I had a function which is just e with nothing to it, again, it's just a number, then what do you think is the derivative of that? I'll just wait for that in the chat. What do you think of that? What is the derivative of e? Yes, it's 0. Exactly. Yep. Not e, it's 0. So again, there is a difference between the function e to the x, which itself then would be its derivative, and then the function itself here, which is just the function e, which is just a number. And if it helps, it's just the same as me writing 2.718 ... So then what is the derivative of this? This is 0. What's the derivative of a number or just a constant? It's still just 0. Okay. So I'm going to, in case 2, would the second derivative be Oh, that's a good question. What I'll do then, somebody's asking about if I took, so in this case here, let me just do, I'll write that again. So the derivative is minus e to the minus x. So if I took that derivative again, it would be itself. So it's minus e to the minus x. And then I take the derivative of the minus x. So this is this is the derivative of the outside function that I just did. And then I have to do the derivative of the inside. So that is minus 1. And so I get a minus 1 times a minus. That gives me positive. So that gives me e to the minus x, or 1 over e to the x. So yes, it does flip from positive to negative. Good question. I like those. I like all questions. But I like the questions where people are curious. It's like, what if I do this? Can I break it? And here's a different question. I have y equals x squared times e to the x. So I have x squared and I'm multiplying that by e to the x, which means that I'll need to use my product rule. And so if I have the product of two functions, that it's the derivative of the first function times the second, plus the first function times the derivative of the second. So that means that for this one, I have the derivative of the first function, so that's 2x times, and I leave the second function alone, plus the first function I don't touch, times the derivative of the second function, which is, oh good, it's e to the x, so it's just e to the x again. A little bit of cleanup doesn't hurt, so I'm left with e to the x, so I can factor that out. And I can also factor out an x. So I'm left with 2 plus x. Oh, I suppose I should have written that out a little nicer. So I got x e to the x times x plus 2. Okay. So to just kind of summarize what I was doing with this chain rule. So in terms of that, what we can say then is if I had some u is equal to like u of x, if I took the derivative of e to the u, that's equal to, again, the derivative of the outside function, which is e to the u, times the derivative of the inside, which is du by dx. Or if you prefer, like, I could rewrite this as something like this. E to the g of x is equal to e to the g of x times the derivative. A new easy exam question. What is the 101st derivative of e to the x? Yep. I probably have seen that question before. It's easy. It's, yeah. So let's do another example. So this one is it's going to be find. Oh, it's a little bit of review right now, right? Find the global maximum value of x times e to the minus x. Now, notice that I didn't give the closed interval. What we'll need to do is we need to look then for a local maximum. And the way that we're going to show that it's a global is that there is some sort of global increase up to that point and some then like global decrease after that. And that's how we'll show that since that's the only point, that must be the global maximum. Okay. So just to make sure, so to find the global maximum, what we're looking for is where the tangent is equal to 0. So we need to find the derivative. So we start out with the derivative. And over here, this is a product. So I have to use my product rule. So it's going to be the derivative of the first times the second plus the first function times the derivative of the second. So over here, so the derivative of x is just 1 times e to the minus x plus, I don't touch the first function, times the derivative of the second function. And because I've already done it, which is over here, I'm going to rewrite it like that. So it is equal to minus e to the minus x, like that. Okay. So then what I'm left with is I can factor out this e to the minus x. So I'm left with 1 plus, oh, and I have the minus here, so it's not a plus, it's a minus. So I have 1 minus, of course, the minus oh, of course. And I'm just left with the x. There we go. There's no importance for the red. It's because I can't write on the tape with this, with the Waterman ink. So I have e to the minus x, 1 minus x. Okay. And now we're going to set this to 0 because we're going to find the critical values. So set f prime to find critical values. Okay, so the thing to note is that e to the minus x, okay, so I'm going to do this. So we'll set that equal to 0. Now the thing to notice about this is that it is always positive because it's an exponential function. So an exponential function is always positive. So that means that it's always positive. So we'll say that this is greater than 0. And over on this side, I have 1 minus x is equal to 0. and 1x. So x equals 1. Okay, so that is our critical value. So just kind of continuing on our analysis on this side right here. I'll have it 1 here, and then I'm going to go from minus infinity to 1, and from 1 to infinity. So what I can do is, with my first derivative here, I can pick a value, say something like 0. And so I know that this is always, well, this is the nice thing about picking 0. I have e to the 0, that gives me 1, times 1 minus 0, that gives me 1. So that is equal to 1, which is positive. And if I pick a number, say like 2, I'm going to get e to the minus 2. And again, that's going to be always greater than 0 times 1 minus 2. And so 1 minus 2, that's minus 1, so that is less than 0. So that means that this whole thing is negative, which means that this is decreasing. So over the entire interval from negative infinity to 1, it's increasing, and from 1 to infinity, it's decreasing. So when we have that, that means that we have a max. And not only that, because it's over the entire, we've looked at the entire global behavior of the function, I can say that f has a global maximum when x equals 1. And what that means then is I'll use f at 1. So that's 1 times e to the minus 1, or 1 over e. That's approximately 0.37. So that's our value. So f has a global maximum when x equals 1, and that value is 0.37. So is everyone okay with that? I know that we're used to looking at it on a closed interval, but in this case, I can look at that it's increasing over the entire interval from negative infinity to 1, and it's decreasing from 1 to infinity. Is that okay? Okay, excellent. So let's do a little bit of a review then, which is about curve sketching. So this is page 6. And so this one is going to be sketch the function e to the minus x squared. Oh, I have my card. And again, on the test, you'll be prompted. Like, there will be questions that says, like, what is the domain? What is the x-intercept? What's the y-intercept? So the domain for this function Well, it's an exponential function, so it still has the same domain as everything else. It'll be over the entire real line. What else do we have? We have the intercepts. So for that, we know already that in general that the function, oops, hopefully I didn't drop the right, over here, that this does not have any x-intercepts. It's always positive. But it does have a y-intercept, and that would be at 0, 1. So we'll write that down. So there is none. But for the y that there is, it's at 0, 1. For a test where we won't have access to a calculator, how are we supposed to compute various values of e? Ooh, Mr. MAE keeps asking the questions. In a test setting, that if you wrote something like e to the 2, that's perfectly fine. That's a number that I can accept. You know, we don't also expect you to tell me what the number for pi squared is. So that's why we're fine with writing. If you're writing something like that, e to the 2, we're okay with that. And anything where we kind of have a transcendental number like that, we don't expect you to write down a decimal number. Does that answer the question? Okay, yes. See, the answer is, if you don't have access to a calculator, then you don't need to calculate what that value is. You just write it down. And that's good enough for us. Right. So, and again, I made, okay. So, and I wrote that right, Mr. Maple. Did I write that down right? 0, 1. Hopefully I didn't flip it again. Is that correct? Horizontal and vertical asymptotes. So, okay, that is correct. Good, good, good. So we got the vertical and horizontal asymptotes. I'm just going to move this card just to my right here while I work on this. Now, there are no discontinuities. Like there's no vertical asymptotes because the function is continuous on its domain. And again, the domain is over the entire real line. So there's no vertical asymptotes. Now the other one that we can look at is these two here. I look at the x goes to minus infinity of e to the minus x squared, and the limit as x goes to infinity of e to the minus x squared equals okay, speaking of horizontal asymptotes, the last assignment brought up, how would we find the horizontal asymptotes for functions such as is that 1 over x minus 3 to the 5th? I'm not. Or was that actually x minus 3 to the 5th? just clarifying on that question. Moment. Because if I just quickly graph it, so just switching over to I have x minus 3 to the 5th, and I don't think that there is any, it's a quintic, fifth, it's a fifth degree polynomial, so there should be like 5 roots, but it's a polynomial, and it should have, it should be increasing, like the range is from minus infinity to infinity, and the range should be minus infinity to infinity. So however, if it was something like 1 over, then it has a horizontal asymptote as well. It should be approaching 0 as well, and so something like that. And you can see that it's getting really, really close to 0. Now, again, it's getting really close to 0 really quickly. And depending on whatever graphing calculator that you use, you might run into some round-off error, but it'll get really, really close to it, but it should never touch it. That's just a quick answer, but again, if you need more clarification about that, we can always talk about that after. So in this case, hopefully that answers the question. Now in this case, if it gets really, really, really big, this means that as x goes to infinity, that x squared, this also goes to minus infinity. So this also gets really, really small. So that's 0, and this is 0. Okay, I thought I saw someone type in the chat. Okay. So that means that I have a y equals 0 is a horizontal asymptote. Ah, yes, it was 4. Oh, okay. I ended up expanding the brackets, but wondered if there was an easier way. There might be. There might be. I would have to just have a look at it. But we can definitely talk about that after class. Make sure you send me an email, and we can definitely chat about that after that. Okay, so we did the horizontal asymptote. Some of the horizontal asymptote is just kind of... Okay, perfect. And decrease. There we go. So in this case, I need to look at the increase and decrease, which means that I'm looking for the first derivative. So to do that, I need to take the derivative of the function. So e to the minus x squared. So I'll just rewrite this again. So it's the derivative of the outside, so again I just kind of rewrite it again, times the derivative of the inside. So I have just minus 2x like that. And if I want to find those critical values, or remember, critical values are where it's equal to 0 or it doesn't exist. So I set that equal to 0 to find my potential critical values. And I get minus 2x times e to the minus x squared. Now that is always going to be positive. And so I'm not going to look at that. But over here, I can have minus 2x equals 0. And then I'm left with x equals 0. So that's my critical value that I need to look at. So I have 0, and then from that I have minus infinity to 0, and from 0 to infinity. So now if I look at that function here, I know that this, I'm going to pick maybe say like minus 1. So like the derivative at minus 1. So I get 2 times minus 1 times e to the minus 1 squared. I already know that this is positive, and over here, minus and a minus, that gives me positive. So that means that this is positive, which means that it is increasing. And over on this side, I'll pick, say, 1 minus 2 times 1 times e to the minus 1 squared. So again, this is still positive. I have a minus times a positive, so that's just negative. So that means that this whole function on this part is less than 0, which means that it is decreasing. Which means then that at x equals 0, I have a max. So there is my fifth one. And in fact, I can see that it's over the entire, I found the maximum for the entire domain. So I know that that's a global. So there's a global max at x equals 0. And so what that means, if I plug that in, e to the minus 0 squared is equal to e to the 0, and any base to the 0 is equal to 1. So that's my point. So then the next one is concavity. So that's my next step that I have for that. 6 is concavity. Page 7. And so what do I look for the concavity? What function am I looking for in step 6? In the chat, this is as a review. What am I doing in, what am I looking for in the second, or in the concavity? Yes, that's right, the second derivative. That's right. I'm looking for the second derivative, and I'm going to use, yes, exactly, and set it. Oh, somebody wrote something. Yes, I will show. For some reason, I don't know why the f double prime that x was, apparently the moderator thought it was, or the Autobot thought it was too sexy. So, we're going to take the second derivative. So I'm just going to rewrite the first derivative just so that we have it in front of us. So we have the concavity. So we got to take the second derivative. So not only do I have to use like chain rule to solve this part here, but I have a product rule as well. Maybe because of the... I'm not sure. Yeah. Okay, so we take the derivative of the first here. So it's minus 2 times the second function. So e to the minus x squared minus 2x. So that's this function up there. And then I need to take the derivative of this. So taking the derivative of just this right here. So that's itself times the derivative of the exponent. So minus 2x. Yeah. Yep. Okay, so the next thing I'm going to do is I'm just going to factor out this one right here. So I got the minus 2 e to the minus x squared. So when I factor that out, I'm left with just 1 minus. I'm left with then a 2x. So I have x and x here, so that's x squared. Now, I need to set this equal to 0. So, to find the critical values, we'll set that equal to 0, which means that, oops. And again, this one over here, this will never equal 0. And in fact, I have over here, this will be a positive, and then I'm multiplying that with a negative, so this will be always negative. So that's always negative. And over on this side, I'm going to solve for where that equals 0. So 1 minus 2x squared minus 0. I'm just simplifying it. Then I'm going to take the square root. So again, applying the square root to the top and bottom. Square root of 1 is just 1, and the square root of 2 I can leave. I don't have to worry about that. Okay, what I mean is I can't calculate that, right? I'm just going to leave it as square root of 2. Maybe I will, you know, if you're not used to working with 1 over root 2, that's plus or minus, that's approximately equal to 1 over the square root of 2. So that's plus or minus 0.707. So from that, I can use those critical points to break up my interval that I need to look at for the concavity. Oops, I'll move that up. So if I picked something like let's say -1. So if I pick something like that, first of all, I know that this is always going to be less than 0. And over here, if I had something like -1, that means that it's 1 minus 2 times minus 1 squared. So 2 times, and that still will be positive. 1 minus 2, so that's minus 1, which is also less than 0. So I have a negative times a negative, which means that this is positive. Which means that on this interval from minus infinity to negative 1 over root 2, that this is concave up. So concave up. Similarly, again, this will always be less than 0, so I'll just look at, let's say 0. So if I did that, then it's 1 minus 2 times 0 squared, 1 minus 0, which equals 1. Now again, I have a negative, negative and a positive, so therefore that this will be negative. So that's concave down. And similarly over here, I'll pick a value, say like 1. So again, that term is going to be less than 0. So it's that's less than 0. And over on this side, I have 1 minus 2 times 1 squared. So that is 1 minus 2, which equals minus 1. That is less than 0. So I have 2 negatives, which gives me a positive. So that means that it is concave up. Why is it negative at 0? Oh, okay. Well, so that's the question. Why is it negative at 0? Oh, at 0. Okay. So maybe I'll write that out a little bit more. So in this case, I'll have minus 2 e to the minus 0 squared times 1 minus 2 times 0 squared. Well, first of all, I know that e, okay, so 0 squared, so that's going to be 0. E to the 0 is 1, so I'm just actually left with just 2. So that is going to be negative. And then I have 1 minus 2 times 0, so that's still 0. So that's just 1, and I'm left with 2. So that's, maybe I'll just leave it like that, because what I've done is I've written out everything. So I'll just kind of erase this part right here, because it might be confusing to some people. But yeah, right here, that's still less than 0. And this part right here is greater than 0. So that gives me a negative value. Oh, we're almost done. There's also additional points if necessary. Nope, we don't need those. Don't need them, because we're going to just sketch that. So, number 8. Sketching. Okay, so I have out my... Oh, no, we didn't quite finish it, because we need one more step, which is the points of inflection. We did the concavity, which is close. Because we kind of get them almost for free. So the points, right, they occur at when x equals minus 1 over root 2 and 1 over root 2. So points of inflection. To confirm, E is always positive when the coefficient is positive, and E is always negative when the coefficient is negative. Yep. I agree with that. What you've said to me is E. Okay, so that is a number itself. So yes, that is 2.718. And then you said negative E, so that's approximately equal to minus 2.718. And this function here, because it's, again, I have e to the x, we know that it's always positive. So if I stick a number in front of that, it's going to make that negative. Okay, so points of inflection. So those occur when we had plus or minus 1 over root 2. So substituting in those values, 1 over root 2 is equal to e to the minus. Yep. Oh, okay. Somebody has put something in the chat. Okay, you have to be very careful of where the numbers were, but I'll get right back to that. We'll finish up this. Squared. And this is nice because I get, yeah, it should be a small positive number, but we'll look at it. Don't worry. Okay, so I have 1 over root 2 squared. So the root 2 squared, it's just 1 over. So it's just negative 1/2, or 1 over e to the 1/2, or that's 1 over root e. Which means then that my point is 1 over root 2, 1 over root e, yes, the reason why, so okay, since it's going on in the chat, what I have here is this part here, this e to the minus x squared, this part is always going to be positive, but I'm multiplying it by a minus 2. So this part, or maybe I'll look at this part right here. So right here, this part right here will always be positive, but because I have the minus 2 here, I have a positive multiplying it by a negative. That means that it's going to be negative. Okay, okay. And similarly, if I do this one, I have a minus 1 over root 2 is equal to e to the minus 1 over root 2 squared. So again, that becomes e to the, I have a minus half still, I got, this is going to be squared. I don't have to work inside here, this will make this positive. So again, I just have 1 over root 2 squared, so that's still 2. So it's 1 over e to the half, still 1 over root e. So there. So now we can do our little sketch. So our sketch looks something like this. Okay, so just kind of looking over our notes, what we had done previously, we know that the domain is from 0 to infinity. We have a y-intercept at 0, 1, so I'll draw that here. I have a horizontal asymptote at y equals 0. What else do we have? We have it increasing. Shouldn't the second exponent end up positive before put in the denominator? This second exponent, I'm not... which one. This is the problem with where in the x equals minus solve. Okay, so on the second one, so the minus 1 over. So in this case, I have a minus here. And I have the bracket, so I have to apply the squared here. So in that case, I have a minus and a minus 1 over root 2 squared. So I'm going to square this. So that becomes, and you can think there's the minus there. So when I square that, that becomes positive. And then I get the 1 over root 2. Okay, so this is squared here, and this is squared here. 1 over, I have a root 2 squared, so that becomes just 2. And I'm still left with just minus 1/2. Okay. Yeah, I mean, I would say that's a common error I see. For instance, I see a lot of people when they do like minus 2 squared, some people will just write minus 4, and that's not right. Because you have to also think of it as kind of like minus 1 times 2. And again, I have a multiplication, so I can apply, just like my exponent rules, I have minus 1 squared times 2 squared. So that minus 1 squared becomes 1 times 4. So that's positive. Okay, so we've got to the horizontal asymptotes. We need to do the next. We have it's increasing and decreasing. So some people might use like something like this, kind of increasing and decreasing. But we also have concavity to look at. So I also know that this is from number 5 here, from the increasing and decreasing, that this is a global max. So something, I'm going to kind of put something like this here. And this is a max. Right, and then I have 2 points of inflection that we found. So, the best part part about sketching is that looks like 1 over root 2. So here we go, 1 over root 2 and 1 over root 2. So it's just going to be point of inflection. Okay, so around there, and 1 over root 8, so I don't know, let's say there. And we're told that it is, between those points it's concave down, so it's got to go concave down. Concave down. At that point it switches and goes concave up. So again, it's still decreasing, but we're going to go concave up. And on this side, this has got to be increasing, but it's going to be also concave up. So something up like that. So there we go. And there's our horizontal asymptote. We've been able to describe most our information. And again, it's a positive, we've got it over the entire reals. We have it that it's the values themselves are always positive. And if you are worried about, you know, if you want to check, if you wanted to use something like the graphing calculator, something that's available through Google, well, we could try that. So it's minus, oh, of course I can't type, x times exponential minus x squared, something like that maybe. That is clearly not the right function. Oh, it's changed something on me. It's put brackets. And yeah, I have no idea what it's doing. This is why we're used to using calculus, because again, sometimes the calculators start to give us some weird funky numbers and I'm not sure what it's doing. It might be the, oh, okay. It might be the exponential. Okay. Let's see what else I can, I'm going to just test it before I start to show it. No, it's doing something odd. I'm not sure what else. I will check just one more other place I could check. Oh, of course. I'm sorry. I know what I was doing wrong. Okay, this is better. What I had done is I had accidentally, you could use math. Oh, no. What I had done is I had punched in the concavity, the second derivative. So what I needed to do was punch in this formula right here. So if I do this, I can just switch back to my screen 1. So there it is. And I can, whoops, I'll zoom in on here. There we go. And it's quite wide. I'm not sure. Yes, exactly. I had punched it in incorrectly. So we can see that, again, it's not very nicely done because I got the scale. I can't fix the scale. But, you know, it goes up to our 0, 1 point right here, which is what we expected. And at negative 0.77, yeah, it should be 1 over e. Looks good. So just to give you an idea of that, we sketched it out, and so that worked. So yes, it did graph the right function. It's just I punched in the wrong one. So this does match what we wanted. Okay. Number 9. Okay, so we have some questions which, you know, should be asking after I've done all this questions. The first one would be, what is the inverse of e to the x? And we can just use our same things that we had used before, except instead of using base b, we'll use base e. So it's log base e of x is equal to y, and that is equivalent to e to the y of x. And as a shorthand, we usually write log base e as ln, or ln. And people are kind of going like, why is it ln? It was short. It's short for, it's from Latin, so it's a logarithm or logarithmus. Naturalis or naturalis. And so that's what we'll use, ln. And it is common on most calculators. So if you have a calculator, there will be ln right there, and there's log. And the log is usually to the base 10. Usually. And so if we have the inverse of that, then that means that if I apply the ln of to e to the x, so this is my inverse function, and there's my original function. So that should give me back just my x. So you can think of that as my inverse function, and there's my original function. So when I'm undoing that original function, then I get my original point back. And same thing here. If I change the order, I have e to the ln x. That's equal to x. And some other numbers that we know, ln e. So I don't have to pull out the calculator. Hopefully we know, because if it's undoing its original one, so ln of e, is it gonna? Do I have to put 1, or should give me 1? And ln of 1 should equal 0. So again, it's just a flipping of it. So again, ln of 0 gives me, no, ln of 1 gives me 0. Okay, so after all of this, I've done we're almost rounding out the end. I'm going to give you in 3 minutes what the derivative, again, this whole start out, which was, what is the derivative of b to the x? Of b to the x. Okay, so this uses the fact, that e to the ln of b, which is right up here, or sorry, right here, e to the ln of b is equal to b. So I'm going to use my derivative. The nice thing about this is I don't have to use the definition at this point. I can just use some of the properties of the natural logarithm. So I'm going to change b, so I'm going to rewrite that so that it's now e to the ln of b. And it's going to be to the x. So I've just replaced b with this. And that is still equivalent to me just writing e to the ln of b times x, like that. And now I apply my chain rule, because again, we're using e now. This is the reason. So, derivative of the first. So, okay, so I'm going to take the derivative of this, of the outside function. So the derivative of the outside function is just ln b times x. And then I have to take the derivative of the inside function, or I take the derivative of the exponent there. Now the nice thing about this part right here is we know that this part right here is equal to b. I still am left with it to the x times. Now I have ln of b times x. But this ln of b, this is just a number. Ln of b, because I fixed what that value is going to be. B is a constant. So that means that it's just, I think of that as just a constant. So if I think of that as a constant like 3 or 4, then it's like a constant times x. So I'm taking the derivative of that, which means then that it's just the constant. And that's it. So that means that the derivative of b to the x is equal to b to the x times ln b. So I'm almost, it's 5:31, okay. So if we go back to the original, where did I put the first sheet? So if I go back to the original sheet here, I can tell you what this is. So the derivative, maybe I'll use a different pen here, of 2 to the x is equal to 2 to the x times ln 2. And down here, this is the derivative of 3 to the x is equal to 3 to the x ln 3. And like ln 2 and ln 3 are fine. So again, if I punched in ln 2, there's that number that's showing up. 693. We're kind of getting close to it. There's a 1, but this is a 2. And same thing over here. Ln 3. 1.987. Thank you for tuning in for our lecture on the derivative of the exponential and logarithmic functions. We have a test on Thursday. Please check out the instructions through Moodle. If there's any questions, please feel free to send me an email through RMC. And with that, I will sign off for tonight. Thank you all for sticking around, and I wish you the best of luck on Thursday's exam, or Thursday's test. Good night.